Hi, friends. We start this course from the design principles of refrigeration. The foundation of refrigeration is removal of heat. When we say refrigeration is basically removal of heat from the space to be cooled. It is not like adding cold. We are not adding cold to something and making it cold. In refrigeration, we remove the heat so that the temperature is below the surrounding temperature, below the ambient temperature. That is called as refrigeration. And the rate of heat removal is our concern. We need to remove not only the quantity of heat, we need to remove a certain quantity of heat as fast as possible or at a given rate. So, the core of heat transfer, fundamental understanding of heat transfer, which is basically a course where you learn how to compute the rate of heat transfer, is very critical in designing the refrigeration. So, the heat transfer through the solid surfaces of the evaporator wall is by conduction. There is a flow across the evaporator coils, that is by convection. Then there is a phase change which is happening, that is during the evaporation as well as during condensation. So in the refrigeration, uh, appreciating that there is a heat transfer by conduction in the evaporator wall or evaporator coil, there is a heat transfer by convection in the evaporator as well as in the condenser, and appreciating how the phase change of the refrigerant in the evaporator and condenser is happening, how much heat they are going to absorb, what is the rate of heat transfer happening there. That is very critical in the heat transfer as well as refrigeration design. Okay, so in the design of heat exchangers, that is of the two components of refrigeration system, this idea of heat transfer is important, which we are going to learn in detail. So our aim of the design would be, one of the aim of the design would be to maximize the heat absorption in the evaporator and to maximize the heat rejection in the condenser, because you know that evaporator is the space where you are absorbing the heat from the space to be cooled, and condenser is a place in the refrigeration system where you are rejecting the heat from the space to be cooled. Okay. The second important design concept is your understanding of the core thermodynamic cycle in your refrigeration system. The core thermodynamic cycle of your refrigeration system is a vapor compression refrigeration cycle. Okay, and the four basic components of your refrigeration system, they are the two heat exchangers, namely the evaporator and condenser, and the two devices which change the pressure, namely the compressor and the expansion device. So in the evaporator, the liquid refrigerant would absorb the heat from the space to be cooled and get converted into vapor. The vaporized refrigerant, the gaseous refrigerant, would enter the compressor, its pressure would increase, its temperature would increase, and the high pressure, high temperature refrigerant from the compressor would enter the condenser. What happens in the condenser is that the vapor of the refrigerant would be condensed, that is, it would reject the heat to the surrounding and convert itself to liquid, and the liquid refrigerant, which is at the outlet of the condenser, expands back to the lower pressure, that is from the condenser pressure, which is the high pressure, to a lower pressure, which is the evaporator pressure. That function is the or that job is of the expansion device like expansion valve or capillary tube. Okay, so the design guide is we need to design evaporator which removes the full cooling load, and we must select the compressor and the capillary which matches the evaporator and condenser heat duties. Okay, that will be understanding as our course develops. The third important principle we need to be learning for appreciating the design of refrigeration system is the properties of refrigerant. Okay, without knowing the properties of refrigerant, you cannot design the refrigeration system. So refrigerant is selected, appropriate refrigerant is selected in the refrigeration system based on its thermodynamic properties. Especially, it should have a high latent heat, it should have a suitable boiling point, and it should be stable at operating pressures. Okay, so this is the important criteria. These are the three important thermodynamic properties. There are other properties also, but these three are important in the selection of refrigerant. Also, chemical safety is important. The gas should be non-inflammable, and the lot should be not toxic. concerns of global warming, concerns of ozone depletion have made it mandatory that the refrigerant which is selected is environment friendly. Okay, so we need to understand these principles also as to what is zero ozone depletion potential, what do we mean by low global warming potential. This also we need to understand while we design the refrigeration system. The common refrigerants which we would be coming across in our design course would be R134A, R600A, and R290. Okay. An important key understanding in your design course of refrigeration system is the understanding of relationship between the saturation temperature and pressure. Okay, we need to appreciate that in the refrigeration system, what happens is that the refrigerant would evaporate at low pressure, that is at the condenser pressure, and the same refrigerant has to condense, that is as to convert itself back to liquid in the condenser at high pressure. That is, at a low pressure the refrigerant evaporates at low temperature. At high pressure, the same refrigerant condenses at high temperature. Okay, this is a core thing because you can change the boiling point, you can change the saturation temperature by changing the pressure. This is a core understanding which we should have while we design the refrigeration system. Okay, and the designers must ensure that the refrigeration system is operating under safe pressure ranges. For example, I have given here example of R134A, where if the evaporator is to be maintained at 0 degree centigrade, the evaporator pressure has to be 1.9 bar. The corresponding pressure in the condenser would be 11.5 bar if the refrigerant is condensing at 45 degrees centigrade. Okay, so whether the condenser is designed to handle 12 bar, evaporator is designed to handle 2 bar, that one has to understand while we design the refrigeration system, and why the evaporator pressure is 2 bar and why the condenser pressure is 12 bar has also to be appreciated from the saturation curve or pH diagram, which we'll be studying in quite a detail. The other important principle, design principle, is the heat load calculations, which will take a significant part of our time in the course. This heat load calculations or cooling load calculations is basically estimating correctly how much heat enters the refrigeration system and then estimating correctly at what rate it has to be removed. Okay, so that total load in case of your refrigeration application, which we'll be dealing in the course, that is medical refrigeration, that would be basically the product load. For example, if you are storing vaccines, then vaccines load, then the transmission load, that is the heat transfer through the walls of the refrigerator, infiltration load, which happens especially when you are opening and closing the doors of the refrigeration system, and then there would be some internal load because of, let us say, some fans or lights which are there inside the cabinet of the refrigerator system. Okay, so this, how to compute those heat loads is crucial in your designing of refrigeration system. Okay, so basically in our course, we will be talking about the sizing, component sizing. We will be talking about the principles which are involved in sizing of the evaporator. That is, how do you ensure that while designing the evaporator, there has to be a correct fin spacing or correct EFPI, how to make sure that the evaporator is designed to give you enough surface area for the heat transfer, how to make sure that there is a proper air distribution in the evaporator. Similarly, while designing the refrigeration system, we'll make sure that how the compressor of appropriate capacity means appropriate HP horsepower, appropriate kilowatts, as well as appropriate displacement is selected, and how it matches with your evaporator pressure and the condenser pressure, how its performance is linked to that. So correct matching with the cooling capacity selection using the pressure enthalpy diagram, all these things we are going to study in our design course of in your refrigeration course. Same thing when you are talking about design of condenser, which is an important heat exchanger and whose job is to reject the heat from the system to the surrounding. Its sizing is also critical in the design of the refrigeration system. By sizing, we mean the correct surface area, the correct fin spacing, adequate airflow through the fans, and adequate efficiency for heat rejection. Okay, so that would be discussed in detail when we discuss take up the discussion on condenser design. Capillary wall, especially the capillary tube, is mostly used in the small capacity systems, which we are going to discuss in our course. How to make sure that these systems are appropriately sized so that there is not no flooding in the evaporator, and appropriate superheat suction superheat is maintained in the system. That also would be a part of our understanding in this course. So, if you appreciate these concepts of the design, we would make sure that the refrigerator which we are designing, the systems which we are designing, they are high efficiency, properly insulated with appropriate sized fans and proper cycling through proper controls. There is a minimal pressure drop, high efficiency compressors, adequate insulation, proper suction super rate, proper liquid subcooling. All these things we can achieve if we understand how the components are sized and how they are integrated well, how they are balanced. Okay. We need to also understand the controls and sepsis systems which are put in place so that there is no uh, shoot out of the pressure. There is adequate protection to the compressor, especially for overload and heating. So that is called as overload relay and thermal protection. There has to be some provision if there is a power failure. There has to be some alarms if there are open doors, if there is a high temperature or low temperature within the systems, and there has to be a proper temperature control via the thermostats and microprocessors controller. Okay, all these things are equally important along with the sizing of your refrigeration system. So, as I said, a proper balance. It is not simply that we are designing individual components. We are not designing a individual evaporator or individual compressor or individual condenser. For that matter, we are designing an integrated system with appropriately sized evaporator, appropriately sized compressor, condenser, and expansion device. If there is an imbalance, that might lead to frosting, that might lead to a very high energy consumption, or the temperatures would be unstable in the cabinet. Okay, so that would be it means that we have not correctly designed and there is an imbalance in the system. So I hope that with this introduction you have appreciated what I'm going to cover in the course, and that would really be a fun. Thank you very much. Bye for now.